Per me oggi presentare il professor Jason Morgan. Jason è stato l'artefice della sintesi di tutte quelle idee e dati che alla fine degli anni 60 hanno portato alla nascita della teoria della tettonica delle placche. Jason è stato per oltre 30 anni professore all'Università di Princeton ed è attualmente professore emerito all'Università di Harvard. Oggi Jason presenterà un seminario sulla scoperta della tettonica delle placche, so the discovery of plate tectonics. Prego Jason, a te la parola.
The history of science, that you see the stumbles and the gradual move forward by people hundreds of years ago up to recent. You get a sense more of what science itself actually is. And one person that I think has been grossly overlooked is Robert Hooke. He was a relatively poor man. Most of the early scientists were landed gentlemen. I mean, Newton discovered his gravity when he was back home on his father's estate, supposedly sitting under an apple tree and looking up at the moon when the apple dropped. One of the few poor people was Robert Hooke, and he was basically an instrument maker, worked with Robert Boyle. Boyle's law is pressure times volume equals a constant if you keep the temperature constant. And you can imagine how you go about doing that in 1700. These great big bell jars that he had made. Hooke made the vacuum pumps that would evacuate it, and you'd put hydrogen in, and in another bell jar you would put oxygen in, and they were on scales and you would weigh them. I mean, it was just incredible how the chemistry grew from really extraordinarily difficult to make measurements with what was available at that time. So this is a list. He made a telescope, was the first person to notice the rotation of Jupiter and Mars. He was the first to observe microorganisms moving around with a microscope. He decided fossils were the remains of living organisms that had been soaked in some kind of petrifying water, and he got into a lot of trouble with this because the church did not believe in extinction. They said God made everything perfect, so why would anything ever have to go extinct? And he also, in geology, said that the fact that you have sediments on top of mountains showed mountains were uplifted. I mean, it's really an amazing variety. And he was in constant competition with Isaac Newton. And when he got into what he's really famous for, the Hooke's law of elasticity, he published an anagram that I show here, CEIIINO, and he didn't want to talk about this because he didn't want Newton to know, because he figured Newton was so smart he'd figure out everything before Hooke had a chance to think much about it himself. And then it was 2 years later that he rearranged those letters to say stress is proportional to strain. And he's not the only one that used anagrams like this. Galileo did once, Huygens, that they wanted to be able to show credit as to the year they had discovered something before anybody else, but they didn't want anybody else to know what they had learned until they had time to think about it more themselves. And that's one of the things that's changed in the last 400 years. Okay, so the main thing I'd like to push here is that science isn't the truth. It's a process for convincing others of the best answer to a question. How do generals decide who is the better general? They do it in a very different way than scientists do, or who's the better lawyer or something. What distinguishes the science is you need the documentation of agreed upon reproducible facts to convince all the specialists. You write papers that contain convincing data. You can't just announce something and everyone say, oh yeah, that's true. It's got to have data. But once the idea becomes accepted, the data is forgotten. The only thing taught in classes are things like F equals MA or volts equals the current times the resistance, and but in science, it's something you might commonly see on your exam questions. There's no credit for the correct answer unless you show all of your work. And so I'm that's the main point of what I want to say. Now the question is, how did I get involved in pushing the idea of plate tectonics and convincing people? And it was absolutely amazing that in about a 1-year period, certainly within a 2-year period, the idea of rigid plates just sort of swept through the scientific world very, very quickly. I mean, the world was sort of primed for this, but it was my paper and several others that just all of a sudden convinced just about everybody. And how did I get involved? One thing is, I had a very different high school math class than most students did. I had the standard trigonometry that deals with sines and cosines, but mostly high school trigonometry dealt with logarithms. And that's because you multiplied with logarithms. You can do multiplication, but it's very slow. It's very prone to error. And logarithms were just the standard technique of doing multiplication. So this is, you see their tables, and you can have tables of sines and cosines. It's just as easy to have the table of the logarithm of the sine and the logarithm of the cosine, and add them and such instead of multiply the different parts. But high school trigonometry is extremely different from college. Now, once and you use slide rules. I bought first day at Georgia Tech buying textbooks. You were expected to dish out $25 for a K&E slide rule, because that's what you used in all of your classes. And in the first week of math at the university, you learned how to do it. Now, I was given my slide rule. I didn't spend the $25. I had a cousin who had been in the Navy, a naval officer in World War II, and he gave me his slide rule. And I'll say that this slide rule has functions on it like no one else's. I knew what, and you don't know what a haversine is, which is half of a versine, and a versine is 1 minus the cosine. And the advantage of haversines is they never go negative. They're always between 0 and 1, and you can't take logarithms of negative numbers. So it was, you could do your star calculations with that function. Now, later, I mean, you can see this is now 65. This is 13 years after I graduated from high school. Calculators were invented, and you could buy one for less than $400. And it was just amazing how what an enormous invention this was for doing mathematical problems. And slide rule sort of disappeared after you could get a hand calculator. And it didn't have a battery. You can see you had to plug it in. But some of the keys, besides multiplying and subtracting and things like that, you could enter a 25 and then a sign key that's one of those little black buttons and get what the sine of 25 degrees was, or go. I mean, they were considered remarkable. Until this, your calculators were great big devices, much bigger than typewriters, and they clanked away, and they cost I don't know, one of the big manufacturers was Olivetti, but these being able to easily multiply and divide and such was an enormous breakthrough for someone who was involved in more theoretical questions. Now, when you went to college trigonometry, it was very different. You didn't mess so much with the logarithms and the actually using sines and cosines to figure how high a tree was by pacing off a distance and measuring the angle up to the top and things. You mainly learned these trig identities like sine square plus cosine square. And it's because these were all very useful when you studied calculus. Your trig class was really a prep course for learning many of the tricks that you used in calculus to evaluate integrals. And that's something else that was very different back in the 50s. I never, I mean, at Georgia Tech, you never took calculus until your sophomore year in college. I mean, nowadays you get it much earlier in high school and such. But my first quarter there, I had test in algebra, and if I didn't meet Georgia Tech standards in algebra, I had to take the course. I passed that. I thought I knew trig very well, But no, the trig was all of these identities and such, not the high school kind of trig. So my first math course was a trigonometry, and I actually got to take calculus the last part of my first year in college, whereas most of my associates, roommates from Savannah and such, never had calculus until their sophomore year, and you never took physics until your sophomore year because you needed calculus to solve the physics problems. But one thing I had in the trig is, we finished the course. The teacher taught 2 weeks of spherical trigonometry, not the plain trigonometry where the sum of the angles is 180 degrees, and spherical where the sides of the triangle or the great circle arcs that connect points. The sum of the three internal angles is 180 plus the area that's included. It's quite different. And this is, I have an example. I can make a spherical triangle that has three 90-degree angles in it. It's this is 1/8 of the total sphere. The total sphere has an area of 4 pi, so the 180 plus that area, the 1/8 of a sphere, adds up. I can have three 90-degree angles, and this also is part of when I took navigation in college. I was in the Navy. I knew how to do this kind of stuff before I got to the textbook on how to compute star fixes and such. I'll mention one of Hooke's inventions is that he invented essentially what is a pocket watch, although it was more like an alarm clock size, where the little wheel and a spring sort of goes back and forth, back and forth. Now, he didn't make it accurate enough to navigate. 4-second error in your clock, and you can be a mile off in navigation. And it wasn't until much later that they made clocks like this that were accurate enough that you could sail from England and get to Jamaica, and your navigation would only be off by 5 miles. And there was an enormous prize and there's a nice story called Longitude about the history of making this particular kind of clock, and so that you could navigate at sea. There weren't radio time signals. Okay, now we'll switch. My senior year at Georgia Tech, and this would be 57. Georgia Tech was given a Remington Rand UNIVAC computer, and the left item in this picture is exactly the type that Georgia Tech had. Remington Rand made a number of these. They sold some to the Army, some to the Census Bureau, and they figured, well, we've sold all the computers we're ever going to sell, and they got out of the business just a little bit too soon. But this is an amazing computer. The one on this is a photograph I took in a German museum, and the one on the right is some German accounting machine. But the left is the Remington Rand Sperry Univac, and all around the outside or the vacuum tubes, there were like 5,000 of them. And then on the outside, so that the heat can radiate into the room, on the inside, they walk through the little door, is all the wiring that connects all of these tubes up in the proper way. The memory on this, and it costs more than $1 million. Well, it cost $1 million when you included the printer that it had. But the memory in this thing is that they had 1,000 words of memory that each had 12 I wrote down characters. I don't know what that means. And it could do about 2,000 operations per second. It was amazing what it could do, but imagine having to spend close to $1 million for a computer that has 1,000 words of memory and can do about 2,000 additions, subtractions, moving from one location to another in a second. The memory was really amazing. It was an acoustic memory that they had a long tube of mercury. It's a nice fluid with a fast velocity, faster than water. And you would have a little ping on one side and a receiver on the other side, and you would send down all of these pings that were ones, and when they're at the specified time, when there wasn't one, it was a zero, and would get to the other end, and a wire, which is much faster than mercury, would carry the signal back, and it would regenerate it. But you would just you would count. You had to know, the place that your bit was either a 1 or a 0, and analog devices like this were quite common in a lot of electronics, a lot of the radar or sonar. That's what this type of memory developed. But just these things, a great big tube of mercury weighs a lot. They would weigh, the floor would be, each of the units would be like 100 or so pounds. This was amazing. I mean, and this is where I learned to compute. I had to write a program for this machine. They didn't let us go and operate it, but we could write a program, and someone who was responsible would test the program. And I remember the program I had to write was, how do you change numbers if you enter them in as the decimal, how do you change it to be the octal numbers that this computer used, so that 10 decimal became a 12 in octal, and then go back the other way. But so this, and it was amazing that there was no programming language. You had to know what the number was that meant add these next two. Then you had to know what the number was that said store that answer in, and you had to have the exact memory location. You couldn't say X or store it in C. You said store this in slot 52 and keep track of it. It was just, it was challenging, but I essentially learned to program a computer in my last year at Georgia Tech at 57. Okay, next. Now, then I had 2 years in the Navy. When I came back to Princeton, IBM gotten into the business by now, and they had this 650 that looked about like this, and this had a funny number coding system. They used decimal numbers, and they took 7 lights on and off to store them. So there's a little console, and when you started it up, you had to toggle in with little switches that you pushed the program that got it started, because that wasn't on any memory. And then your memory was essentially punched paper cards. You could have all of your data, and you could have your program. And so there's on the right where the person is the computer and the memory, and on the left is the card reader, the card punch. And you'd carry around these boxes with 2,000 cards in them. You'd keep one on your thesis work under your bed at home, so it'd be perfectly safe. Wouldn't get messed up, and you know, to lose a large part of your thesis work would have been terrible. So yes, under the bed in our house, there were always copies of what my thesis was on, and I had one of the earliest sort of more computational theses in physics. That's now a whole area, but and what I did was incredibly simple by comparison with modern stuff. Then these little magnetic core memories were discovered, and they're little ferrite rings. They're about the size of, they're smaller than, I don't know, Cheerio cereal, little oat crunch rings with holes in them. And they were magnetic. And if you put a big enough current in the middle, it would magnetize the loop. But how you use this as memory is that you had 2 wires going through, and each one carried about half of what was needed to make this thing flip. from one magnetization to the other. And if you wanted to know what the memory was at one place, you would essentially send a current of half enough to do something through, say, one of these horizontal wires. You'd send half through a vertical wire, and there would be one cell in this whole array of little wires and rings where there would be enough current going through to make it flip. And if it flipped, you knew that was a 1. And if it didn't flip, it say was a 0. And then you would send the current back in the opposite direction to reset it if it had done any flipping. But these were amazing, and they only cost about a penny per bit. Not the tens of thousands of dollars that, say, the Mercury tubes had, or the IBM 650 had a spinning drum that it had a 2,000 word memory, and it took about 50 milliseconds to go around once. In fact, if you were a good programmer, you would add 2 numbers, and you'd make sure where you were going to store it was a number just after the 2 that you had picked up and added, so you didn't have to do a complete revolution of the drum to store it. And that was fancy programming. Now, there were all of these young women with nimble fingers and sharp eyes in Taiwan that made these arrays, and it cost about a penny per bit, which is just an incredibly low price compared to the tens of thousands that you would spend. But I want to show you at the bottom is a little disk that has 8 gigabytes on it, laid on top of an actual photograph of one of these cores. Now, if you wanted 8 gigabytes at a penny a byte, that would be $80,000. I mean, your early memory was just extraordinarily limited. I mean, you thought 2,000 words was, wow, that's an enormous computer, unlike what you have today. Okay, now that's computer. That's part of my education. And now we go into the plate tectonics. And this really was invented by Harry Hess. There's a photograph of him at the blackboard. He backed away from the continental drift of continents plowing through and on their leading edge, crumpling up, and behind he essentially emphasized the use of a lithosphere. And now this also Walter Alsasser, who was a physicist that was my postdoc advisor, was very much into material properties kinds of calculations, made a big point of. But the idea is that the ocean floor, as well as the continents, moved away from the spreading ridges. And then where there was a trench, they came together, and the ocean side went down underneath the continent. And this is basically plate tectonics. Now, he gave a talk at it was the presidential address of the Mineralogical Society section at the American Geological GSA, Geological Society of America. And he gave the talk. He wrote a paper for this that was to be published in a book that actually came out 2 or 3 years later. The book was a collection of papers by students of his thesis advisor, Arthur Buddington. And books took a long time to come out. And so he made about 200 copies on a mimeograph machine. I have one of the copies, and distributed them, mailed this to people he knew at Scripps and Woods Hole and all of the people that were interested in the sea floor. And what's amazing about this paper is that there is absolutely zero data in the paper, or new data. And I told you that the key of science and convincing people is you have to show the data. You need it. And what he had instead, I mean, he just said, we know these things about the ocean. Look, they can all be explained if you just think of them as passively moving on top of a lithosphere. This sort of replaces and modifies the ideas of continental drift and but at the end of this paper, where he summarized everything in the oceans, it said, look, this idea sort of fits this, is that he had at the very end what he called the recapitulation, and he said, if what I've said is correct, then I can make these predictions. And he listed 19 predictions of what this model was. Now, I have had the nerve to give him a grade. You can see that almost every prediction he made has a little green check mark. There's 2 that he absolutely missed. He thought the ocean crust was serpentine. And that's because at fracture zones, that's commonly what you dredged. And serpentine is stable to about 500 degrees Celsius. And if you go down about 5 kilometers, you get to that kind of temperature. And he thought the sharp boundary that you observed seismically at 5 kilometers was a change from peridotite to serpentine. He didn't recognize that it was basalt. So his reason for the uniform thickness of ocean and suggesting that it was serpentine was incorrect. And then he's sort of right on numbers 4 and 9. But it's just, I mean, this is extraordinarily powerful to sort of stick your neck out and make predictions of things that you were considered to be generally true, but that they were all, he was showing that they were consequences of his idea of the crust essentially moving at exactly the speed of the lithosphere below that. And it didn't matter if it was ocean crust or continental crust. So there's a picture of Harry again. He was a captain of a ship in the Navy, ran resupply missions 4 times from Hawaii to the Philippine Islands during the invasion there. The other photograph is my postdoc advisor, Walter Elsasser, who was a very renowned physicist in many different fields. He was involved in Earth's magnetism model. He calculated the Elsasser tables that are used by atmospheric scientists as to what spectral line is, not just carbon dioxide but of all of the different molecules, sort of using Raman spectroscopy kind of approaches. How do you calculate how a molecule of many different things, what particular light frequencies it absorbs or emits? He was calculated weather. World War II, he was calculated what the weather in the North Atlantic was. He was stationed in the Empire State Building and was there the night that the B-26 went through the 88th floor, and he was on the 44th floor. And he said he walked down all the stairs in the dark, 44 down to the street. And when he got there, he realized he had left all of these classified maps of what weather measurements in the Atlantic was. And he said he shrugged his shoulders and said, no German spy is going to walk up 44 floors to get into my office and look at that map. I'll take care of it tomorrow. Okay, well, this is from Hess on all these trips, kept his echo sounder going. He decided the idea that you should turn off your echo sounder was a ridiculous rule. It wasn't an order that you had to, and so he didn't. And he crossed these flat top seamounts in the Pacific, named them Geos. This is the first one. And okay, and that's sort of the where plate tectonics starts. Okay. So in January 1967, I had been in the geology department about 2.5 years then. Bill Menard at Scripps published a very short paper in Science, and in his book, Marine Geology of the Pacific, he was very emphatic that the great fracture zones in the Pacific Oceans were all great circles. And in this paper, he said, I was wrong. They're not. And to show that, he drew them on a map of the Pacific that was a mnemonic projection. And that's also called the Great Circle projection. And if you put a light source at the very center of the Earth, and you say the Earth is transparent, and you shine that bright light and it goes through onto a flat piece of paper, any great circle will be a straight line. If the plane, a plane that cuts through the center, cuts through the sphere, will be a great circle. When that plane strikes a piece of paper, it's going to be a straight line. And so he published this map, and on the one on the lower right said, look, they're not all straight lines. Therefore, the Clipperton, some of them are sort of straight, but the Mendocino's not, and you get further south into the Pacific, they're not straight lines. And I saw the figure. This is in January 87. And I said, they're probably concentric circles about a common pole. And this is a better map of that. You can see that 7 and 8 are sort of bending down. 2 and 1 are bending upwards. And it was just sort of almost an exact copy of a picture that was in my navigation textbook in the Navy. The left shows you what a mnemonic projection is, and then there's the corresponding map, and the equator that goes through Ecuador, is a straight line, and all of the meridians that go from the North Pole to the South Pole are great circles, and they're straight lines, but the lines of latitude aren't. And I realized you could use this and find out where was the pole that made these. And this is the drawing that I made. You can see we didn't have Xerox machines back then. This is some kind of a wet copy, and I tried a number of different places and found that if you put a pole at 78 north and 111 east, you could pretty much go through all of those curves, being straight down by Mexico and Central America and bowing upward to the north. And so, these great fracture zones in the Pacific all had a pattern about some point in Siberia. Now, that point in Siberia had no significance. The Pacific had moved, but the idea was that when they were made, they were made as something concentric, and that I knew about. This is a cleaned up version of that. One of the key things that you learn in physics mechanics is Euler's theorem, and it essentially allows you to calculate the motion of a body as all of the linear forces acting on the body make the center of mass move, accelerate in a certain direction, and the torques about that center of mass will give it a rotation acceleration, and it allows you to it's a two-step process. Calculate the motion of bodies, both the arc they travel through, and then also how they spin and rotate. So the Euler's theorem was going back to about the 1700s, is a really important part of mechanics. And what I did by showing that these were rotations.
Dad, how did you calculate the dotted lines in the previous circle? What did you do to do that?
So I assumed there was a pole a number of places. I kept redoing it. Say 79 north, 111 east, and I would choose a longitude and would calculate, well, what latitude at that longitude is, this fixed distance from that pole that was in Siberia. I mean, this is a whole bunch of, calculated a whole bunch, used a computer to do it, a whole bunch of latitude and longitudes that points that were some fixed distance from my test pole. And you would assign it a longitude, and then you would calculate, well, what latitude at that longitude will be, so many degrees from Siberia.
Okay.
I mean, it was.
Okay, thanks.
So, about every 5 degrees I calculated and plotted a point. And you made maps by hand. You didn't. Princeton in particular had no capacity at all for doing graphics. That the Oceanographic Institutes did. Is that clear?
Yes. Yes.
Okay. Now, the point of this is Euler's theorem describes rotations of fixed things on spheres. And so Hess's idea was that the ocean was rigid and didn't deform and such like this. And this was a test of of his idea. This could, you could almost take as proof. I mean, if the ocean distorted while it was opening up, you'd get a mess compared to these pure sweeping arcs. And the Pacific didn't mean anything, but the Atlantic did. And so the next thing was to go to the different fracture zones in the Atlantic, and that's the upper right picture here. And you could calculate one pole that fit all of the fracture zones in the central Atlantic, from the Azores down as far as the tip of Central America, essentially. And you can see on the top that you can fit that. Now, the bottom is those curves are the opening to get Brazil up smack against Africa. And over the whole opening of the ocean, it's not just the present motion that makes the present fracture zones. There's some other initial openings, but that's the test, and that's what I get credit for, is that if Hess's idea that the oceans behave perfectly rigid, didn't deform, just moved away from each other, if they deformed, this would be a mess. And the fact that Euler's theorem could explain the pattern of all these fracture zones was essentially a test as to how rigid plates actually are. I mean, I didn't really invent plates, but I said, if they're not rigid, this doesn't, this is, you couldn't do this. And so that's the that essentially was my contribution. So I published a paper. You can, I finished it when I was at Woods Hole the summer after this. Made a map of the different oceans blocks. This is sort of the first map that shows what the plates were. Was a figure in that paper. And this is sort of the key sentence. We now make the assumption that gives this model mathematical rigor. We assume that each crustal block is perfectly rigid. If it's rigid, then it's going to move according to Euler's theorem. If the hypothesis is true, the conclusions will be in accord with observations. And so that's sort of the key statement in the paper. At the same time, Lynn Sykes was looking at focal mechanism solutions, not fracture zones, but of earthquakes. And you could use those to infer, not the actual map of a fracture zone, but where you got compressive waves or dilatational waves as first arrivals. You could you could look at points that a ship hadn't been at on the left is the fracture zone, so at about 60 north and 30 west, there's sort of a pole. The earthquakes are not as good. They don't really disagree, but there's a lot more scatter. The magnetic anomalies was another case that as you go from north to south, as you get near the Azores, the spreading rate is slower. As you get down into the South Atlantic, the spreading rate is faster. So this was one of the figures in that paper. It wasn't just the Atlantic. You could go up the San Andreas Fault or into British Columbia, Alaska, and these are the top are actual fault strikes. The bottom are earthquakes. The earthquakes aren't as clean as looking at exactly what the fault is, but it's not just the Atlantic. It was somewhere else. And Walter Pittman had just finished his surveys with the El Tanin in the southern part of the Pacific, and he sent me a copy of what he was doing, and said I could use it. And you can see that the magnetic anomaly rates of the different El Tanin cruises suggested that the Pacific was moving away from the part on the right that's part of the Antarctic plate that fit the same kind of curve, that the rigidness really worked. I had been very impressed with Hess's predictions, so I tried to make some. These weren't very good, and the error bars are way too big. The measurements today would not tell you what the but I did the closure. I mean, Africa, I knew how North America was moving with respect to that from the San Andreas. I knew how the Pacific was moving from North America. Down with Pittman's work, I knew how Antarctica was moving from the Pacific, and therefore I could presumably predict how Antarctica and Africa were doing. And so I made that prediction. This doesn't quite agree with more modern data. The accumulated errors were too big. So I never mentioned my office mate was Fred Vine. He came to Princeton shortly after he graduated from Cambridge University. We shared an office for 2 years and were across the hall, sort of on the same floor for the next 3 years. And I learned a lot of what I know about geology in the oceans from Fred. In fact, Fred was my translator. I couldn't really understand Hess because he spoke petrology, and Fred knew what it was, and he would translate and tell me more exactly what some of the finer points of what Hess was saying was. I would have had a harder time without Fred's presence. I did not thank Walter Elsasser. That's because he taught me what I knew about geophysics, and I thought what he taught me is what everybody knew. But no, it was unique. It was unique, Walter. I was too ignorant to know that, and I do wish I had given him appropriate credit for the real strong lithosphere, and that just seemed obvious to me that he said that's the way it was, and I believed it, and I didn't know that most people didn't believe it. Okay, one last little bit, and these are a number of the papers. There was a paper that said exactly what I said by George Bacchus that was published about 3 years earlier. It's a little one-page paper, no figures. It was in Nature. He has all of the key points that I have. Nobody believed him. There's no data, particularly in the paper. And when I was in '69, when I was working at Scripps, George came up to me and gave me a copy and said, "You probably have never seen this," which I had not. He said, "Nobody has." But he really he said it, but he didn't back it up. Just a little note. He said he thought about writing an NSF proposal to digitize some magnetic lines in the South Atlantic to show what he was saying, but he got interested in his inverse theory and seismology and did that instead. Now, another paper that came out in Nature in December '67 was by McKinsey and Parker. Dan came up with the idea quite independently. He was at the AGU where I gave the talk, but he had left the meeting. The meeting was running over. I went into lunchtime, and a large part of the audience left just before I gave the last talk of the morning. But he published in Nature. I submitted my JGR paper in October. At the as I was leaving Woods Hole, JGR takes a very long time to publish. Came back and I had a few revisions, but anyway, it took about 6 months to come out. So my paper, even though I've submitted it long before his between when he submitted and when it was published was only 2 weeks in Nature. JGR is slower than that. Xavier wrote a very long paper, very detailed, published right after I did. And then Isaac Oliver and Sachs did their tour de force of seismology, and these 5 papers just sort of really took the world by storm. And by the time Isaac Oliver and Sachs' paper was published, almost everyone believed in the rigid plates. So this is George Bacchus's entire paper. when you write papers, don't write them this short. Include some figures. But if you read it, he says everything he says is correct. And that's my story. I hope you have questions, and I'll try to answer them if you do. When you do.
Thank you, Jason. So the way we have thought about going ahead would be to have a question and answer moment, probably in I don't know, a week or 10 days.
Okay.
Or so, and the students will let me know when that would happen. Anyway, I have a couple of questions, if you don't mind.
Okay.
To finish. I mean, there are two very standard questions. The first one is, what do you think where do you think plate tectonics is going? What would be the next big thing? I mean, there are lots of things that are still
No, it's you needed a model. You know, you assume the plates are rigid. You can calculate how they're going. I mean, you have some magnetic anomaly rates. Rigid, you can calculate. You don't have to calculate anymore. GPS tells you what these plates are doing. There's the measurements are simply incredible. How many there are, and how you don't need to assume plates are rigid to calculate where they're going. You just measure the way they're going. A GPS station in India, and you know how fast it's moving towards the Himalayas and such. So it's sort of like you used to could only calculate problems that had perfect geometries, and you had mathematical functions. You could do spheres, you could do cylinders. Now you can do airplanes. Something really complicated shape going through the air with computers and numerical methods, and it's just being forced to have simple geometries to solve fluid mechanics problems is a thing of the past. You can go after the most complicated problem possible with finite elements or other numerical techniques, and GPS has done that. I mean all of the space geodesy methods work. The laser ranging to the moon, or very long baseline interferometers and things, but GPS is portable and cheap, and they're probably 10,000 points of the Earth that without having to make any assumptions. So the modern is just go out and measure something.
So probably in that respect, some of the ocean geodesy that now is coming up would be quite interesting.
Now, ocean geodesy, you sort of need an island. to put your instrument on. There was once an attempt at Scripps to have markers on the seafloor and a buoy anchored but floating that would ping and know where it was with respect to the other, the things you had put on the floor, and that you could see how the Pacific south of the Aleutians was, going, and how much it lurched when there was a large earthquake. And there was a lot of money spent on that by Scripps, trying to develop a way that in the ocean itself to measure how the seafloor was moving. But that's sort of been abandoned. You just you probably use it's in the oceans. It'd be the only place that you use the rigid plate calculations, that you'd make measurements on Hawaii and some of the atolls and things, and assume it's rigid and think how fast it's going under the Aleutians. Not a direct measurement, because you've got buoys anchored on the sea floor south of the Aleutians that you're using GPS somehow to see where they are. Is that clear? Or
yeah, sure, absolutely. Well, the second question I have, one of the points that often come is about mountain chains and how they might not follow rigid sort of plate.
Right. No, you can completely abandon the idea that it's rigid, because you can go and make the measurement. You know how fast some little town in Nevada is moving, and it's not exactly the same speed as say Kansas City or Denver. You have basin and range spreading, and your GPS is much more accurate than any conventional geodesy. There was a time they were using the early surveys on the Transcontinental Railroad and comparing those to modern surveys to make estimates as to how much extension was going on in Nevada. But now you can measure it in just a couple of years with GPS, down to millimeter per year kind of accuracy.
Watching at this system, though, with a geologist's eye, GPS, in a way, they give the instant motion, which might be quite different from the long-term motions.
Right.
So probably you still need some of the calculations that, in the same way that you have done.
I don't think so. I trust the GPS more than the rigid plate model. It's actual. It's what's really happening. It's not a prediction.
I have a different
question. You don't predict what a person's temperature is when they walk into a hospital. You stick a thermometer in their mouth, and then you know.
I have a question or curiosity that we've had plate tectonics now for however many decades, and we are still somewhat debating about the driving mechanisms, about why the lithosphere is moving the way it is. And do you have any thoughts about why progress has been relatively slow in terms of getting a consensus and a real dynamical understanding that everyone just sort of agrees is obvious?
No. No, I don't think there's an easy answer to that. I mean, it's a good thing there are problems left.
Okay.
Okay, well,
I think a really interesting problem is the glacial rebound right now. I mean, and so much of Earth science is 50 years ago. It was sort of a time of the solid Earth and convection and things like this were the really dominant problems. I mean, the paleontology was losing its primary position in geology. I mean, when I first got to Princeton, there were 5 paleontologists in the department, and right now with the retirement that just happened, there's 0. And solid Earth seismology, plate tectonics, and things became more dominant, and now the emphasis is more towards climate, and so the connection between what you and I do and modern, more climate-oriented Earth is tied up in the glaciers and the rebound and and GPS is a very useful tool in that.
well, thank you for now, and so see you in a week on 10 days with a student.
Right.
Okay?
Yes.
Well, thank you.
Bye-bye.
Bye-bye.
So.